Hi, I wanted to go back over the most recent Chapter 3 class. This is the one where we talked about quantum numbers and also electron configuration. I wanted to draw a quick picture at the top just to try to give an overview on the quantum number idea again. Remember, this is what I'm drawing is the Bohr model, the planetary model. It's not a correct picture of the model, but it is one that's actually possible to draw in about, 15 seconds. So that's why I'm using this model. All right, so what I'm doing right here is I'm just throwing some electrons on our atom. The point of quantum numbers is that I can pick an electron that I want to talk about to some other person or that I want to do calculations with. And instead of having to say that I'm talking about the electron on the first energy level that's in the s orbital that is in the up spin direction, I just use quantum numbers. And it's kind of like saying that this is the ticket that this electron has. So first energy level, s orbital, there's only one type of s orbital, and then I'm talking about the up 1/2. So it's kind of like these ones are telling us where, and then this one's telling us which one. And if I moved over and I was talking about this one, then I would use these numbers. Because again, first energy level, it's the s orbital. There's only one type of s orbital, so it's the one labeled 0 and minus 1/2. Now I could also switch to the second energy level, and I could say, okay, so now I'm talking about the 2. I'm still going to talk about the 0 one for this one, so that's s. And there's only one type of s orbital, and I'm talking about the positive 1/2. I'm randomly picking these because the electrons are really moving, and this picture doesn't clarify the shape of the s or the p orbitals. So then I'll say, oh, and this is going to be the other s orbital. Oops, sorry, it's negative. Because I already made this one over here the positive, so this one is the negative one. And then on that second energy level, there's also just enough room for some p electrons. So then I'd say, okay, so this is the one that's 2. Now see, look, I'm saying it's 1 because it's a p. And then I can pick one of 3 numbers that goes in this middle section because there are 3 types of p's. As to which one, I'm just randomly picking them. If I were actually doing some majorly fancy calculations, I would actually use more information than this. I would say something like I'm talking about the px one rather than using a 1. And then the last one, I can decide, okay, that's the up 1/2. And then I can pick another one. So let's say that that's the one that's paired with the other guy, the one I just did in red. So 2, 1. If he's paired with him, he's still in the same p orbital, and it's negative 1/2. So what the red is saying, it's kind of like if we have 3 p orbitals, and I call this one 1, I call that one 0, and I call it minus 1/2, then I'm saying that the one over here on this side is going to be like my up 1, and I'm saying that the one over on this side is my down 1. Now, for that to be true, I have to already have the other 2 orbitals filled, and I do. I'm just haven't labeled them yet. So, like, I could call this one, again, second energy level, the p, and then I could make that one be like the 0 electron. And I could, pick another one and have it be one of the other electrons, 2, 1, 0, minus 1/2. That would be his pair. And then, but remember, you would fill them singly. It's just I've already drawn a completely filled up p orbital. And then like this one would be 2, 1, minus 1, 1/2. And so that would be like that one. And last but not least, have I shorted myself? Oh, here he is. That would be his pair. 2, 1, minus 1, minus 1/2. This walks through these numbers. So these numbers are kind of like a code or a fast way of talking about the different electrons. And usually this is, again, used for people who are just calculating things. So the first number in the series of 4 is your N, and then you have your L, and then you have your M sub L, and then you have your M sub S. So this is the N, and this is just your energy level. We also will call it a shell. Remember that energy levels are specific and unique for each atom. Then we have our L value, and remember when L is 0, that's an S shape that looks like a 0 looks like an S, like a sphere kind of. And then you just count up from there. You could write this on the side of your test just to remind yourself so you wouldn't get confused in the middle of it. And I think I said this before in class, I don't like that example, how they wrote that. So I usually will write that L is equal to n minus 1, comma, and just whole numbers down to 0. So this has to be whole numbers. And these values are what we have that I've listed over here. This is the subshell. Again, it's telling us the shape of the orbital. And the orbital is the region that we find the electron. So it's basically the electron, and the way it's moving really, really fast is the ultimate shape that it ends up taking, or in that space. Then we have our M sub s right here. And most people like to see these as the capital L's. This is also whole numbers. And M sub L is equal from your positive L all the way to your negative L. So what we do is we're going to be picking one, let's say like this one. It's whichever one you're going to be talking about. So if I was talking about the D's, which is L equals 2, my M sub L values would be 2, because it's, and we can write it like this, negative 2. You'll notice right there. And it's all the whole number values to the positive value of L. Or if I had L was equal to 1, so that would be talking about the P up there. If I had that one, then my M sub L possibilities are 1, 0, minus 1. M sub S, I'm sorry. It is M sub L. At the very beginning, I totally meant to say M sub L. Wish I knew how to edit these faster. Okay, so what this is talking about when we're looking at these, it's like when we have a P, we have 3 kinds of orbitals that they call them degenerate. They're equal energy. 1, 0, minus 1. So those are the orbitals that P could be found in. It correlates to, like, you could call this one like the one up and down on the z-axis, and then one is on the x-axis, and then one is like, and this is hard to do, like that's coming out towards me and that's going back. That's the y-axis. Or however you do your axes. And then if you're talking about like the D, then it would be over here. And you could do negatives first or positives, they don't care. And this corresponds to the different D shapes. They kind of have like a double dumbbell shape, most of them do. They're on different axes also. It's just really hard to draw them like on the like, so there would be like on the maybe a flatter axis. To me, these all kind of look the same. And then there's a funny one that kind of looks like it's got like a spiral in the middle or something. And then there's one that's drawn up and down. So anyways, it tells which of those that guy is in. And again, I do apologize. I totally meant M sub L. And then the last ones are our magnetic quantum number. That's because our electron is like internally, like not internally, but he's like spinning on his own axis. So he's a negative charge spinning on his own axis, and he has a magnetic field that's generated. So you could call the side the north of the magnetic field, and this is the south of the magnetic field. And what happens is that when the electrons go in, if you want to call up as facing north, you can. Again, it's generically decided you could call it south if you wanted. But the idea is that like the one with the field that's north, or the one that's, let's say you're going clockwise for one of them, the electron that comes in with him, he has to be going counterclockwise, depending on which way you're looking, or clockwise, counterclockwise. And we represent that like that. So at least their poles are correct. But they still are flying around like crazy in that shape, like all over the place and stuff. But when you put something in orbital, it has to be paired like that. If you want to know more about spin, this is a great video. Okay, now I wanted everyone to get rid of this row. This is just a confusing row. It doesn't need to be in there. So 4, that is our energy level, which is the N value. That one's 4. And like over here, the 5, that's our energy level. So that's really easy. And then we don't have anything, but right here we have that this is 4, so we can put a 4 in front. And those are our N's. Now, this is telling us that we have an F. So when L is 0, that's our S. When L is 1, that's our P. When L is 2, that's our D. And when L is 3, that's our F. So that means that L is 3 because it says F. And like down here, this is D. So that's when L is 2. And this one right here is telling us L is 1. So as a little note, we'll put in parentheses. This one is the P. This is the D. And that is the F. And then for M sub L, those again are from the positive L values all the way to the negative L values. So there are multiple possibilities of what these could be. Sorry, I can't count downwards and talk. 3, 2, 1, 0, -1, -2, -3. And you would just pick one unless there was more information in the problem that said, oh, we're talking about the one that's 0 or something like that. You just randomly pick one, or you say it could be one of these. And then for the P, it's from this, this, or that. And again, you can write the negative first. No one really cares. I mean, they do care, but not for Gen Chem. People have their own stylized ways they like to do it. And then this guy's just the spin. And again, you would say it's either positive 1/2 or negative 1/2. And as a little note on this over here, your L's can get bigger, and the letters just keep going. So like if L were 4, that's G. If L were 5, that's H. If L were 6, it's I. It keeps going. All right, so what orbital is described by N equals 3, L equals 2? So again, the first thing, the N, is always, it means the third energy level, or it's the third quantum level. And then when L is 2, remember from up here, when L is 2, it means a d orbital, so it's a 3d. And it says M sub 1. This would be enough to get to your answer. If you were trying to be like really, really specific, you could do something like this. And then you could say, oh, we're talking about this one. But most people don't go that specific on our test. We're only going to have you go to here. And then it's actually only one of these is not allowed, because there's actually 2 that are allowed. So the whole key is that anytime you have an N, the N should be a whole number. And it needs to be not 0, because you can't be on the 0th energy level. There is no 0th. It always starts at 1. So all of these are not 0, and they're whole numbers. So those are all good. Then the second thing with your L's is you just need to make sure your L is a positive whole number less than your N. This is okay. He's less than 6. This guy's okay. He's less than 6. And this okay. He's less than 3. I meant to say that this guy is less than 5 and that this guy is less than 3. All good. Then what you want to do is you want to check that right here, M sub L goes from positive L values all the way to negative L values. It can include 0. This is where we have the problem, because if our L is 0, the only possibility for M sub L is 0. It cannot be 1. So this is our one that has the issue. Over here, if L were 4, all the possibilities are 4, 3, 2, 1, 0, -1, -2, -3, -4. So 0 is definitely one of those, so that's fine. And then over here, This last one, the L values were 2, 1, 0, -1, -2. And look, he's in that grouping, so he's cool too. So B and C are fine. More practice. Don't miss out on the practice. All right, so for electron configuration, there are 3 principles. The oddball principle, this is building up. And the idea is that you're going to have to fill the lowest energy orbitals first. And that just means, like, if you've got a nucleus, like, you're going to fill the places close to the nucleus before you fill the ones farther away. Partly because that nucleus is going to pull anyone in towards it if there's nothing in that space of this orbital right there. So you got to fill the 1s. You can't fill the 2p way out there before the 1s. The exclusion principle, it just means this is the one that's related to you need to have your arrows opposite. They can't both be up when you're in your ground state. If you were to do them both up, they would end up with the same quantum numbers, and you can't have an atom with them having the same quantum numbers. Every electron is unique. And the last one is Hund's bus rule, and the idea is that when you get on the bus, and if there's someone in one seat and there's an empty seat, you're probably going to go into the empty seat. Same thing with the electrons. So if there is something right here, then the next electron that comes in, he's going to sit in an empty seat. And then again, in both these cases, if there's already someone here, it's not going to sit there. And if you happen to have 2 people, again, like, it's not going to sit here. Part of that's repulsion. They've got repulsion energy in this space. Although they will pair, but they just don't do it until after we've gotten everything filled and we're not having to deal with repulsion. All right, paramagnetism is when you have an unpaired, at least one, if not multiple, unpaired electrons. That would make something magnetic. And dimagnetism is when you have all paired electrons. So for Gen Chem, we would say not magnetic, but you could also say that it repels a magnetic field. And so if we're looking at these examples, if I wanted to compare this to this, because they both have 2 electrons, and like this would be 2p2. So I'm looking like at the end of these atoms. Let's say these are the only electrons that we're worrying about. This would also have already had filled the 2s, and he also would have had his 1s filled also. But when I look at these, so the ones that matter, there are the ones at the very end. This guy right here on top, this is what we would say diamagnetic. And then this guy over on the bottom, this is what we would call paramagnetic. All right, so we're going to keep going. So the way these work is you're going to start right here. You're going to go this way. You're going to fill it. You're going to go here. This just goes with increasing numbers on the chart. So like this is 10, this is 11, like that. This is 2, this is 3. And you fill them with electrons. We'll show some examples. And what these relate to are energy levels. So like this is the 1s energy level that's right here and right here. And we have to fill those before we can fill like the 2s and the 2p. So there's our 2s and there's our 2p. And then we have to fill those before we can fill our 3s and our 3p. See, those are higher energy levels. And then note that there is something funny that happens right here. So we have a 4s, but then we go back to our 3d. There's right there. We're going back to that 3D. You need to know that that 4s and that 3D, they are super, super, super close in energy. Remember, as we go out from the atom, the orbits get closer and closer, and they are close enough that they can move between them. And the 4s actually ends up being lower energy when it's empty than all of those 3Ds. There's multiple orbitals right there. They're super close in energy, though. Super, super close. All right. So just as a reminder, if we're doing hydrogen, that's doing this one right here. That's hydrogen. I'm going to undo him. So we would just say that there's just one electron right there. If we're doing helium, that's the guy over on this side. And he has an electron here. Whoops. He would have an electron here and an electron here. Both of them, notice, is still called 1s. But they are going to actually look like that because they can't pair, both of them being up. So it kind of depends on how you want to write these. Here's some more lithium. So lithium is right here. So he's going to be a 1s1, a 1s2, total of 2 in the 1s. And then there's going to be another one in the 2s2. So there. And then nitrogen, he is over here. His 1s's are filled, his 2s's are filled, so you can see there's an electron here, an electron over here, here, and then he's right there. I'm sorry, I just did that for hydrogen. Or helium, I did it for helium. There we go. And that's nitrogen. So just seeing the energy levels. It's going to be easier for you to do it this way, though. You want to do it with the periodic charts. This is where you're starting. And neon is over here. So you've got an electron here, an electron here. So it's 1s2. You've got an electron here and here. Actually, though, remember when you do it there, it should be opposite spin. And then here we've got 3 p's, and then we have 3 more p's. So 2p6. That's neon. The sodium, the block is in the wrong spot. He's supposed to be right here. That's where he is. So again, we've got our 1s2. We've got our 2s2. And then we have our 2p, 1, 2, 3, 4, 5, 6. 2p6. And then we have our 3s1. Now we've got vanadium. So 1s2. We've got our 2s2. We've got our 2p6. We have our 3s2. We have our 3p6. We have our 4s2. Then we have 1, 2, 3. 3d3. Then we have our arsenic. It follows the same idea. So 1s2 is going to be filled, so we're to here. And then our 2s2, I guess I'll do them in. P6, 3s2, 3p6, 4s2, 3d10, and then notice this is a p. It goes back up to 4p. 1, 2, 3. You want to be able to do it where you're not actually writing the arrows in, and you won't. You are given that like these rows are rows that are numbered on the side. You're given those. You aren't given that this is the S block, so you have to memorize that one, and that like this is the D block. You aren't giving those. You have to memorize those ones, and you have to remember that this has the little drop down. A lot of times I would just write it right there, so I'd remind myself that that's where the drop was. I would just write them all in there. Okay, so there's your shortcut, so you don't have to write all this all so long. So this is sodium. So sodium, we did sodium up here, right here. We did sodium up here at the top. And we've got all of his electrons in. This is the orbital notation where you're drawing them with boxes going horizontally across. The pink part represents another element. You'll notice that is actually him, which is neon. You can use a noble gas to cover this section of sodium. Or, like over here, this actually matches up over here with argon. We still have to do the 4s2 and the 3d3. And then again, argon, 4s2, gotta have the brackets. Well, it's not right without the brackets. 3d10, 4p3. So noble gas core saves us a ton of time, makes things easier. Okay, so if we look at vanadium and arsenic, and we do the noble gas configuration, that's what these ones are right here, we're going to talk about something that does happen. Like we've got vanadium and he's all super cool in there, but we have kind of two exceptions you need to know about. That it's two of the columns in the transition metals do funny things right here. So if we look back at helium, nitrogen, and neon, there is stability with half filled and fully filled orbitals. So for example, like an S that's fully filled, that's more stable than an S that only has one electron in it. But it doesn't really affect things until we get to the Ds. So here with our Ps, like half filled is going to be better than just like those guys. And then fully filled is the best of all. They're more stable is the idea. And the elements either want to arrange so that they could be like these guys. In the S block, it just slightly affects something called trends. That's for the next test. And the P block, it does strongly affect trends. But in the D block, it actually affects the configuration. And it happens right before half and fully filled D block elements. And I realized that it would probably be easier if we were to just use, instead of the energy level way of doing it, it'd probably be easier just to have it written out from the chart. So I'm going to go up to one of these charts up here. If you look at vanadium right here, to get to chromium, it's just right. Chromium is just right here. All right. He is almost half filled. So if we had an electron right here, that would be D5. So chromium is almost but not quite half filled. Super close. That's the situation that we can have an issue. And also like right here, this is a fully filled D. So right here. And it's actually the columns, and some of that column too is affected by this. So these are like the special spots. So you'll notice if this is vanadium, chromium's configuration, and I'm going to copy it over to the other. The chromium configuration is you would expect it to be this. See, it just has the one more electron in it than the vanadium did. So I'm going to grab him. I'm going to copy him down. Oops. I'm going to bring him back to where we were talking about it, which is over here. So here's chromium. This is what you predict. And if we were to draw that picture out, it would look like this. So the thing is, though, is there's some major stability going on for the D block. If you take this electron, and if you get rid of him here, leave a hole. So do you see the hole? Leave the hole, and you move him over to here. That actually happens, because remember, they're really close to each other. But it only happens when you are almost half filled. I showed you the columns. So this right here is your actual configuration. It actually becomes argon 4s1 3d4. This is the answer, not that, because of this picture right here. And I'll copy it down so we have it on the next page. And again, the way those electrons look, everything down here is filled. Okay, and then we've got one electron here, 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 here. And then the other one that was here is not there anymore. And he got moved over to here. That's what happened. And then copper, the same thing's about to happen. What you would maybe expect for copper, if we go back up to that same picture up here. Copper's over in this place. So you would expect everything to be filled. This was the chromium one. And the copper one, that's Cu, Ar, 4s2, 3d9. So see, he's right here. He's almost 3d10. That's the other place it happens. I bring it down to here. This is what you would expect again, but it's not what happens. So here's our 4s part of it. And there would have been an electron here, but he got bumped up over to here. So this is not our configuration. Our configuration is AR 4s1 3d10. And like I said, this only happens in those two places on the chart. You don't have to worry about it happening in the other places. And again, picture-wise, that's all filled. Here's our, I'll put a purple. Here's that electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that, I'm going to make him green, though. That 10th one is going to be green. That's the 10th one. And like I said, it came over like that. All right, make sure you know that. There'll be something like that on there. Last but not least, ion configuration. So ions is just when you have a different number of electrons than the one that they ask about. So ions are charged atoms. They become positive. So if you're making a positive one, by losing the negative electrons, or they become negative by gaining negative electrons. They do this so that they can have half-filled or fully filled subshells usually. So they have some motivation kind of similar to what was going on up here. But these are actually losing electrons or gaining electrons from to someone else. So they have extra electrons to work with so they can get these configurations they wish they had. In the case of fully filled S or P blocks, they can have half or fully filled valence electrons. They're extremely stable when they have those, and they are low energy. Not like they drop way down, but it's more stable to have everything all filled and paired up and happy than to have some random ones, like some being filled and some not filled. Okay, so isoelectric atoms, this word right here, you need to know this word. They are different elements with the same number of electrons. They do not have the same amount of charge. So they don't have the same amount of charge. An example of an isoelectric atom would be helium and lithium plus. Helium, like if we're looking, so he's 4,2, and this is neutral. So this has 2 protons as well as 2 electrons. Lithium plus, so he's normally 3, let's call him like 6,3. He's normally 3 on his protons, you can get that off the chart. But when he's positive, it means he's lost an electron. So he has 2 electrons also. This is isoelectric. Notice that they are different elements and that they have different charges. All right, so cation example. Look back at the example of sodium from earlier. Sodium prefers become positive because it's a metal. It will lose an electron. So the neutral configuration that we had for sodium that we did way up here is right here. So sodium plus is the one that's lost an electron. He has one less electron. The electron is going to come from here. So sodium plus's configuration is 1s2, 2s2, 2p6, and that's it. You don't write it like you don't write that. You don't do that. You just stop where the electrons are. Notice now he looks an awful lot like helium, right? Not helium. He looks an awful lot like argon. Neon is the one. So how does changing the number of electrons make it a full shell? Do you see how, like, now that we've lost that electron, now we're full? And the total number of electrons that this guy has is 6 plus 2 is 8 plus 2 is 10. Anion example. So look at the example of nitrogen earlier. So we did nitrogen up here. Where is he? Right up here. So this was 1s2, 2s2, 2p3. Go on down. Here's his configuration. And if it's negative, it prefers to become negative. It's going to gain an electron because electrons are negative. Now, this would be an example of him gaining one electron. So if he just gains one electron, again, you would add it to this area, 2p4. Now, this is not a fully filled shell. It looks like that. That's not all the way full, and it's not half full. So he actually isn't happy stopping there. So if we wanted to have a full octet, he needs to gain a total of, he gained this one, he needs to gain a total of 3. And if you look at the valence number of electrons on the chart we've been talking about, it does show that he likes to have a total of 5 valence electrons. 3 of them would be coming from here, and he has 2 in the S. So the configuration of N minus 3, this is him gaining his 3 electrons, is 1s2, 2s2, 2p6. Because notice that's where we would add our 3 electrons from. And his total number of electrons that he has, if we were to add them up, is 6 plus 2 is 8 plus 2 is 10. So if you look up, we already said this, that sodium had 10 electrons, and nitrogen minus 3 has 10 electrons. So yes, they are isoelectric. So you also need to understand right here about the D block transition metals. They are a little bit different. Like all metals, they prefer to become positive. So they will lose an electron because the electrons are negative. So when they lose the negative things, they become positive. And the D block metals have 2 very, very closely spaced orbitals. Again, we keep mentioning this 3D, the 4s. There's also the 4D and the 5s they're close to. Here's what happens. It loses from the 4s before the 3D. And this feels a little weird at first because we filled the 4s and then the 3D. So it feels like we should come out of the 3D, but they don't. It's an energetics thing. So the example of cobalt, it prefers to become positive. So again, we keep saying this, it's going to lose an electron or 2, however many it's going to lose. So the neutral configuration of cobalt, we did it earlier. I think we did it earlier. Or maybe we didn't. We didn't do them earlier. Well, you're going to want to get out a periodic chart. You're going to want to look up the neutral configuration of cobalt. It's going to be argon, 4s2, and I do not have a chart sitting right here beside me. I'm pretty sure that he's 3d7. I'm trying to remember if manganese, what comes after manganese? It could be 3d6. It's going to be whichever one is on the chart. I'll make a little note at the bottom of the video at this point as to whether that's 3d7, 3d6. We're going to assume that he's at the 3d7 position because it doesn't matter as far as understanding what happens. So if this becomes cobalt plus 2, this is the crazy bit. It's going to come out of this guy. So he has 2 electrons, and if it's plus 2, it means that we're losing 2 electrons. So the way you write that is AR 4S0 3D7. We don't actually write the 0, so the way we really write it would be AR 3D7. That is the configuration of that one. Or for here, again, it comes out of the S first, and after we've run out of S electrons, so up here, that's 2 of them, after we run out of S, and then it can come out of here. So that's the second choice, and this is the first choice. So argon 4S0 3D6. And again, you don't write the 0. Argon 3D6. And if you're not sure about these, you could easily, like if you want to try a few of them, you could easily Google, like try doing iron plus 2 and iron plus 3. And if you Google their configurations, they come up right away. And you can make sure that you did it right and that they came out of the right spots. So just as a reminder, check yourself. Do we use 2 total quantum numbers to label the location of the electron? No. You need a total of 4 quantum numbers, and the first 3 tell us where the electron is, and the last one tells us which it is. Is the N the shell and the L the subshell? Yes, true. The L quantum number indicates the shape of the orbital. That is also true. It's the S, P, D, or F. Can the spin of an electron be 1 or 3/2? No, that's false. Is the orbital described by this and this a P? Well, it is the third, but when L is 2, remember when L is 0, it's an S. When L is 1, it's a P, and when L is 2, it's a D. So no, that should be a 3D, so that one was false. Is it okay to pair electrons before filling each orbital singly? That would be false. That is not okay. Br is the element that has this configuration. Okay, it might seem like he has that configuration, but he's a whole energy level below there. So this is not the configuration of Br. This is the configuration of chlorine. So that one's false. That's a good tricky one though. Orbital configurations use lines or squares filled with arrows. Yes, that's true. Paramagnetics have at least 1 unpaired electrons and are magnetic. That is also true. A positive ion has more or less electrons than the neutral. It has, if it's positive, it's lost some negative thing, so it has less. And then a transition metals fill the 4s before the 4d. It does fill them, the 4s before the 4d. And F minus, when you go back and you do the configuration, you'll see that that is also isoelectric with neon. One final little note on some of this configuration stuff for the ions. If you are feeling fancy about things, you could also look at where sodium is on the chart. So if we go up here, where was our sodium? Right here. See how he's right here? If he's positive, it's like he's gone back to being him. Then you could just do his configuration as the positive configuration for sodium. You don't have to do it that way, but I'm just throwing it out there because I have had people ask. That's kind of the second way to do it, and it's totally fine to do it that way. All right, this is a long one. Good luck. Hopefully that cleared up any questions.